So now we will do this example on hypotheses testing. Example: a sample of 30 students study for an average time of 4.1 hours per day. The population standard deviation is 0.5 hours per day. Check the null hypothesis that all students study for an average of 4 hours per day, except a 5% chance of making a type 1 error. So that's all the information we need to do this question. What we'll do is we'll start drawing it out so we can get a visual of what's going on. So basically we have the population of students, and what information are we given? We're told that they have a sample of students. In fact, so this is your sample right here. I have a sample of n equals 30 students. They also tell us that the average time that this sample of 30 students spent studying, x bar, is equal to 4.1 hours per day. They want us to take a 5% risk of making a type 1 error. So remember, alpha represents the risk of making a type 1 error. They want us to set that at 5%. And what else are we told? We're told that the population standard deviation, so let's put that up here because it's for the populations. So that's the symbol for population standard deviation, sigma, and we're told that that is going to be 0.5. Okay, so basically what we need to do is find our region of reject and do not reject. We need to put the hypotheses down as well. But so what is our hypothesis? Our null hypothesis is that students study for, the average time that student studies is 4 hours per day. And the alternative hypothesis, HA, is that the average does not equal 4 hours a day. So we're going to come up with our regions for reject and do not reject. And so our do not reject region is going to be somewhere in here, centered at 4. So if students study for close to 4 hours a day, it's agreeing with the null hypothesis. So in that case, we're going to say do not reject our null hypothesis H0. If we fall in the red zones over here, we're going to say reject H0. If our sample falls in the red zone, and if our sample falls in this red zone, we're also going to say that we're going to reject H0. Reject H0. So the question then is, okay, so what is that point there then? That cuts off the reject and do not reject. What are these critical points right here? And we already established earlier on in the earlier video that we just need to apply this formula. It's going to be mu of H0 minus the number of standard deviations we need to be away from the mean. So in this case, well, let's do it more generically. It's going to be Z of alpha over 2. Remember what alpha is 5%, so this could be Z of 2.5%. And we're going to multiply that by this population standard deviation sigma. We already know that's 0.5 divided by the square root of the sample size. So that's the low critical value. The upper critical value is going to be the same as this, with the exception that it's going to be a plus in here. So it's going to be mu of H0 plus z of alpha over 2 times sigma divided by the square root of n. We know what most of these things are. Mu of h0 is just the value that comes from the mean from the null hypothesis. That just says the mean from the null hypothesis. Well, the mean from the null hypothesis is just 4. Z of alpha over 2 is going to be z of 2.5%, which we're going to have to calculate in a second. Sigma, we're told, is 0.5, and we're already given that, and the sample size was 30. So the only thing that we really need to work on a little bit is going to be z of alpha over 2. Alpha is 5%, so z of alpha over 2 is going to be z of 2.5%. And we already know that z of 2.5%, we already established this earlier when we were doing confidence interval, that's going to be approximately equal to 1.96. And basically you can just do a norm.s.inverse to get that value in Excel. So we can just do, that comes from, I have to put that in parentheses, norm dot s dot inverse of 0, 0. Let's raise that a little bit. Remember, Excel wants all the area to the left, so if the area to the right is 2.5%, the area to the left is going to be 0.975. Okay, so now we can actually, now we know what z of 2.5% in, we can go ahead and fill in the values into these two formulas. And so I'll just do it down here. So mu of h0, as we said, is the mean that comes from the null hypothesis, h0, and that's going to be 4. So this figure just right in here is going to be 4. And then from that we're going to subtract z of alpha over 2, and z of alpha over 2, z of 5% over 2, z of 2.5% is 1.96. And then we're going to multiply that by the standard deviation, population standard deviation, which is 0.5. And we're going to divide that by the square root of the sample size. And we said the sample size gets up here, where they told us it was 30 in the question. And then we're going to do, that's going to give us the lower critical value. For the upper critical value over here, we're going to do exactly the same thing, except there's going to be a plus in it. So it's just going to be 4 plus 1.96 times 0.5 over the square root of 30. And once you crunch those numbers through, you're actually going to get this lower critical value is 3.82, and this value here is going to come to 4.18. And these are, I can actually go back up here and put them in here. So this is actually 3.82. And this critical value up here is going to be 4.18. All very good. There's only one more step now to see if we should reject or not reject. We're going to take our test statistic, which is the bunch of students that they told us, the 30 students actually studied for an average of 4.1 hours. And we're going to see if our sample test statistic falls in the green zone or the red zone. And in this case, 4.1 If this is 4.18 and this is 4.1 is somewhere around here. So this falls in the green zone right here. So our conclusion is do not reject H0. If we do not reject H0, it means we go with H0 and not with the other alternative. So this is how you do hypotheses testing. What I'd like to do now is show you a slightly quicker method of doing this same question. People often just don't want to go through all this calculation. They want to avoid doing these calculations to find these critical values. And in fact, when we just did this question, the actual distribution we were using was X bar. So this was a distribution of averages that we spoke about earlier. It involves quite a bit of work. The beauty of doing it this way, that we actually did it, however, is that we can relate to all the numbers. You know, the hypothesis is that students study for 4 hours per day. I've got a feel for what that means. They took a sample of 30 students who in fact studied for an average of 4.1 hours a day. And I know that's pretty close to 4. And with me accepting a risk of a 5% chance of making a type 1 error, I know so long as my sample of students study somewhere between 3.82 and 4.18 hours average per day, it's going to be close enough to agree with the null hypothesis. So basically, this question, the way we've answered it, is using the original units, the average hours per day spent studying. And so we can relate to it. We can relate to the critical values, the hypotheses test. We can relate to the sample as well of 4.1 hours per day. Questions are very rarely done using these units. What people want to do is they want to cut down the amount of work they do. So what they do something that looks fairly similar, but instead of using the X bar units, they want to change over to the Z units. And the Z units are the standard normal units. So they just want to rescale it. And the reason they do that actually saves them doing a lot of work. So if we're trying to do the same question, again, it's going to look very similar. Look, I'm just going to try and line this up. There you go. That's going to be one critical values there. And the other critical value is going to be here. And the do not reject zone is just the same between these two critical values. So it's between these two critical values here. This is the do not reject zone. Do not reject H0 zone. Have you noticed that the test that we do, you either do not reject H0 or you in fact reject H0. The test is always done on H0. See here, reject H0. And over on the other side is also going to be a reject H0. It's kind of interesting. We never really talk about the alternative hypothesis, HA. We just run a test on H0. Now, when we want to go from using the original units of the question, the sample mean units, the X bar units, and we want to change over to using the Z units, we just have to go through the same transformation process we use for the normal distribution. And the transformation process to go from X bar to Z is you take all of your X bar values, so right over here, this is a transformation process. You take your X bar values. From each X bar value, you subtract the mean of H0 that you get from H0, which in our case is 4, and you divide out by the standard deviation of a sampling distribution known as a standard error, which is sigma over the square root of n. So what does that mean to us? That means that all these values, to go from X bar to Z, must go, all these X bar values must go into this equation. So the 3.82, what does it become down here? Well, I put the 3.82 in here, I subtract the mu of H0, which is 4, and then I divide by sigma, which we said was 0.5 divided by the square root of 30. And if you do that, what in fact ends up happening is you end up with a critical value down here, let me just scroll a little bit, of negative 1.96, which happens to be the number of standard deviations you need to be below the mean to generate a 95% confidence interval. And if we do the same thing on this side, if we take the 4.18, put it into this equation, 4.18 minus 4 divided by 0.5 over root 30, this figure over here becomes 1.96. In fact, the actual critical values are just going to be, in this case, minus z of alpha over 2 and plus z of alpha over 2. So your critical values are far easier to calculate than what we calculated up above before. The critical values were mu of h0 minus z of alpha over 2 times sigma over the square root of n. Now it's just going to be minus z of alpha over 2, and similarly on the other side. So it's a lot quicker to come up with the critical values when you use the z-axis or the z units. The only other thing that we have to keep in account of is that the test statistic here is in the x bar units, and the test statistic must also be transformed into z units to be consistent. I can't just say now the test statistic is 4.1 and 4.1 lies somewhere out here, so the conclusion is changed from do not reject to reject. No, the conclusion must be the same. So we have to standardize the test statistic as well, put it in the z units. And again, it's simple. All we do is we take the 4.1, we put it into this equation, we subtract mu of h0 divided by sigma over the square root of n, and we're going to get the standardized test statistic. And before I do that, let's just note, what does the 4 become? When I put 4 into this equation, it's going to become 4 minus 4. This value in here is actually going to be 0. So let's go back and work out the standardized test statistic. We can't use the 4.1. So as it is, we have to standardize it. So the 4.1 is going to start off with the 4.1. To standardize it, we must subtract mu of h0, which is 4.0. And then we must divide out by sigma, which we said is 0.5, over, the square root. Let me just rid of that. Divided by the square root of the sample size, which is 30. Note, when you do this calculation, be careful. I'll put that in parentheses to make it somewhat easier for you, but be careful that you do it the right way. Otherwise, you're going to get a wrong figure. So this minus this divided by, be careful when you do this calculation, the result should come out as something like approximately 1.09. So your standardized test statistic is in fact 1.09. So it's not 4.1 as it was before. So where does our test statistic lie? So 1.09, where does it lie? On this scale, 1.09 is going to be somewhere around there, which is very similar to what we had before, and it falls in the do not reject region. So you see, falls in about the same spot as it did before on that scale. About halfway between these 2 points, is about halfway between those 2 points in there. And that's it. So most people actually do these tests using the second method, and that's the way that we're going to be doing them on the exams.